Wave functions.
Say again, wave, we're talking about wave functions, yes. Remind me what we said about wave functions way back in the beginning when we very first talked about them. What do wave functions do? What do we need with them? Prior to the 1900s, how did we predict the future?
The crystal ball.
Okay, that one doesn't work as well. Our way doesn't work great, but that's just made up. So, how do we as physicists predict the future?
We need equations.
Differential equations, right? And what do we need to know?
Initial conditions.
Initial conditions. We need to know P0, and then if we only want the velocity, we're fine. If we want the position, though, we typically have to do another integration to get position as a function of time, which necessarily means we need that initial position. So when they tell you asteroid Bennu is on its way to collide with the Earth, be afraid, run, run, that's where that comes from. They know the forces, they find the initial conditions, they figure out where it's going to be sometime in the future. Why did that go away in the 1900s? Okay, it didn't completely go away. We can still talk about asteroids, but we do have a lot of trouble if we're trying to predict what those are doing. We can't predict their future that way. Why not?
Because you can't know.
You're in there, you can't know something.
You can't know position and momentum at the same time.
Better than some tolerance. And we talked about bouncing electrons off of each other and how we can't, if we know that they go this way, I mean, we basically don't know what path they take, right? We know they go in, we know they come out, but we don't know which one goes where. Basic constraint. So this idea of a trajectory, that's what goes away. We can't write trajectories of things and tell where they're going to be in the future. So how do we predict the future? If trajectories go away, if knowing r as a function of time goes away, what's the only game in town now, for those at least? We get close with asteroids and planets.
Probability?
We can say things about probabilistic, we can make probabilistic statements, although it sounds like it's not deterministic, but it's not. That's a false statement. I'll talk about that in a second. What gives us those probabilities? First word you said in class.
Wave functions.
Wave functions tell us those probabilities, right? We have equations that allow us to get the wave functions, and the conventional wisdom, the idea, the motif, the central dogma of physics is in that wave function is everything we can possibly know. Can't get it from the wave function, you can't get it. And so that's where we are right now. And what I'm in the process of doing right now is trying to bring some appreciation for the idea of exchange. And there's a lot of talk in this section, we're in chapter 17, there's a lot of talk in this chapter about exchanging particles and what are the rules and that kind of thing. So that's basically where I am. And so we are talking about what kind of particles. Just lately, right? We've said over the semester we've talked about a lot of different kind of particles. I get that, and it's going to get worse. I'm going to bleep over most of the weirdness of the brand new particles, but there's going to be tons of them, and it gets out of hand, and so you start trying to look for anything you can find to bring order out of this chaos. So we'll talk about some of the things we do. One of those is the idea of exchange. What happens to the wave function if you exchange particles? So what are we talking about just lately in that context? What was I writing on the board? It's writing stuff on the board.
You're looking at particles with different spins.
Not any spin, it's spin 1/2, right?
Yeah.
So I was talking to, the simplest way I can get at this that I can find is a spin 1/2 particle. And that's because a spin 1/2 particle can be spin up or spin down. Doesn't get any easier. And the fewest number of particles I can have where I can talk about exchanging them is two. I can have one particle, but then it's nuts to talk about exchanging it, right? Two particles, I can exchange the two particles. Two states, doesn't get any easier. So it gets worse, but it doesn't get any easier. And so these were the two spin states of a spin 1/2 particle, plus z-axis, minus z-axis. And in fact, what I'm talking about is the z component. I don't think I mentioned that last time. I think it was very clear about exactly what I was talking about, but I'm talking about the z component of the spin of this particle. And you're gonna take my word for some other things, but I'm gonna try to show you this part. So what's special about this gave this a special name. It was called a ket. So this ket, if this operator operates on that ket, what's unique about this combination of operator and ket is that I get the value of that spin and I get back my same ket. This is called, this is a set. Think of that as a set. The operator, the function, ket, and the value, those come as a group. They're a family, as it were. Anybody guess what I'm going to get when I apply that same operator to this spin down ket?
Negative
Yep,
spin.
good guess. And I get back my same one. And when it turns out I can build this whole algebra out of having the x component operate on that and the weirdness that happens there, and we find out basically that I can know the spin along one direction, and I can find the total magnitude of the spin, but that's it. I can't have the x and the y and the z. More of this uncertainty problem that I have, but a more general idea of the uncertainty. I can have a certain set of things that I get to know. If I know those, there are other things that I don't get to know at the same time. If I change my mind, I can measure one of the other ones, but then I lose the knowledge I started with. Anyway, I talk more about that. If you're going to be in the modern, we talk a lot more about that at the beginning, and in quantum, the full-blown quantum class, obviously. So this is for one particular particle. If it's in this state and I apply that operator, I get that state. What I'm claiming is that if I now do an experiment on this electron and measure its spin again, I'm always going to get that. And that was seen in the experiment where you put the electrons through the magnetic field, and they would bend, instead of bending any possible direction, because the spin could be any direction it wants, they would only go up or down. So that's how we got this idea of weirdness of it can only be up, it can only be down. If it's in between, it won't stay there. If I put it in the up state, it'll stay there forever. Put it in the down state, it'll stay there forever. If I put it in one in between, it won't stay there forever. So again, that idea of stationary states versus any state. Okay, now I want to talk about two particles. How do I write a ket of two particles? I could, for example, do it this way. If you want to, you can think of that as a function of x times a function of y. They're independent of each other. And I want to know the spin of the two together, the total spin of that state. So what do? I apply the spin for particle 1 and the spin for particle 2, and I add them. That's going to be the total spin. So that seems sort of intuitive. The thing to keep in mind is that the spin for particle 1 only acts on ket for particle 1. The spin operator for particle 2 only acts on the function for particle 2. If you want, think of this as a derivative with respect to x and a derivative with respect to y. The derivative with respect to x only affects the x function. The derivative with respect to y only affects the y function. And the other one is a constant as far as it is concerned. So when I apply this, S1 affects that 1 and gives me plus h bar over 2. Am I writing it the same way? Yeah, half h bar over 2. And my ket for number 2 stays around. Plus the spin operator for particle 2 that affects only the function associated with particle 2 gives me another h bar over 2. With my function for particle 2 back. Particle 1 was just along for the ride. Well, what happened there? I know you're scared, but it's not any worse than it seems.
You're just getting H bar.
I get 2 h bars over 2, plus 1 h bar, and my function back. I've been doing that all the way through my notes. Constantly putting a 2 where it doesn't belong. And a 1 where it doesn't belong. Everybody sort of get that? I mean, whether it makes sense or not, get used to it, because this is the way you do quantum mechanics. And we're going to be doing a lot of that over the next, I don't know, week and a half or whatever we have left of class. So if I have a function, if particle 1 has a spin along z of h bar over 2, and particle 2 has a spin along z of h bar over 2, it seems intuitive that I have a total spin along z of h bar. And that's how I make that statement. This is how I get away with making that statement. The total z component of angular momentum, of spin angular momentum, for this state pops out this number with my function back again. So I can say with confidence, yes, I know the state of this system. It is plus h bar and it stays that way forever. I'm going to do a few of these, and then eventually we're going to exchange the particles. But I gotta this is me building up to that point. If you had to guess, what do you think you're going to get? I mean, you should do it, but just speculate.
Just
Look,
the particles back, no H bar.
I will get h bars. Remember, SZ is this. SZ is these two operators added together. It's the total z component of the angular momentum.
Is 1/2 H bar minus 1/2 H bar?
And
0.
yeah, and 0. Does that seem intuitive? That I got one pointing up, one pointing down? Yeah, it seems to make sense that it's 0. What's the difficulty with that? We talked about this a little bit last time. What's the difficulty with that state, or right there? Here's a hint. Tell me what this state is. What is this telling you?
You got one particle spin up and one particle spin down.
Not that. And that's the point. It's not telling me that one of the two particles is up and one of the two particles is down. What is it telling me?
A specific particle.
Particle
Spin.
number 1 is up and particle number 2 is down.
Oh, so you can't
You
know
can't
both.
differentiate.
And as far as we know, yeah, that's rule, right? Rule. We live by rules in physics. You can't know. You can't know. So you must write a linear combination. I'm going to do that in a minute, but I want you to think about why physicists who are famously rule breakers must. If this one's not a problem, nor is the first one I read. This one's not a problem. This one, which is minus 1 H bar, down, up, no, down. Why is that not a problem? Why is this one not a problem?
Because they both have the same spin.
Yeah, I know that one particle is up and one particle is up. I know one particle is down and one particle is down. Yeah, that's not telling me which is which. This does. So again, why must a physicist do one thing and not another thing? So I'm going to do that. I'm going to make a linear combination of these. And I want to do SZ of that. This one was up. 2 is down. This is 1 is down. 2 is up. So now I'm not making any unfounded claims about knowing which particle is which, right? There's a probability that one is up, there's a probability that one is down, and I'm hedging my bets. But this has two operators, right? S1 and S2. So when I do that, how many products do I have? S1 plus S2Z onto 1, 2 plus 1, 2. Well, that's just FOIL, right? All you gotta do is FOIL it. But you gotta be careful about what's foiling what. So I will have this term, I will S1Z onto up 1, down 2. I'll have S1Z onto down 1, up 2. I'll have an S2Z onto up 1, down 2. I'll have an S2Z onto down 1, up 2. Tell me what to write down. What do I get from this first one? S1Z acting on this ket, this combined two particle ket.
And H bar over 2.
I get a plus H bar over 2 onto 1 up, right? S1 onto 1 gave me this and my ket back. Down 2, just hanging around. Somebody else tell me the second one.
Minus H bar over 2, and then both of them are up.
Minus H bar over 2, and then that's this one?
Yeah, because both of them would be up, right?
No, this is an eigenket of that operator, so you get the same ket back.
Thought we were turning the down ones up.
We're not changing any kets, and so, let me see if I can see what I did here. So when I did S1 onto this 1, I got plus H bar with my up ket back again. And the up 2 just hung around. Plus S2 acting on that ket. That gave me a plus H bar over 2 because it's been up. That up 1 hanging around, and S2 on 2 gave me H bar over 2 with my 2 back again.
I think
Yeah,
you're talking about last class, right? Like the end?
no, that's something I wrote
Show me what you wrote down. See if I must have written that wrong. Let me check my notes. You guys check that.
This is the last thing I wrote from last class.
Yeah.
Yeah.
And that's me going off the reservation.
Okay.
That should be down. S on down gives you that minus h bar over 2 down.
Okay.
I just wasn't being careful. So, in the language of quantum mechanics, these are eigenfunctions and eigenkets, and they go together, they make a family. And when this operator operates on this ket, it doesn't change the ket, it gives you a number. I said those words, but I apparently wrote something wrong on the board. Did I write that again today?
That we turned that upside down as well.
What's that?
I said it seems so intuitive to turn it upside down.
Yeah, and I mean, that's the dangers of intuition in quantum mechanics. What I find is that you can build intuition around this weird stuff like relativity and quantum mechanics, but it takes a while. You really gotta grind a lot, in Dr. Moyer's words, before you get to, oh yeah, that's kind of intuitive. And so intuition is what you're used to. You get used to this. You don't ever understand it. It never makes sense, but you do start to think that you intuit what's going on. Okay, so is this clear? And did I do that earlier this class? He showed me from last, I did it again this class earlier?
Yeah, I had it the same in both classes.
Can you show me from this class? Because I want to get it fixed. So up goes up. Yeah. Again, because we're working with these families, the operators and the kets are eigenfunctions and the eigenvalue. That should not happen. The worst part is it does happen. Right? If we were going to start looking at x components of spin and y components of spin, they do change. They do flip back and forth, and that's why it's a natural problem to worry about. Today, I'm trying to very carefully never do that, and apparently I failed already. All right, so plus. Let's do the next one. Given the clarification
H
that
bar over 2 under ket dice.
so I think you said plus h bar over 2. And where am I? I'm doing this.
I thought minus, yeah.
So this on this, you're telling me minus there? And it's h bar. And my up
And the ket.
1 is just hanging around, and I get my down 2 again because this is an eigenfunction of that operator. So, plus there's one left, right?
H bar over 2, 1 down, 2 up.
H bar over 2, 1 down, 2 up. Is that right? Everybody okay with that? So now let's group our terms. We have up 1, down 2, up 1, down 2. We can group those. So that's h bar over 2 minus h bar over 2 onto up 1, down 2 plus. There should be a down 1 and an up 2. Yes. There's a minus h bar over 2 plus h bar over 2 up, down, 1, up, 2. Did I do that right? Down 1, up 2, minus h bar over 2, down 1, up 2, plus h bar over 2. And I can factor that. That's where I started from. And I can factor these out. I have an h bar minus 2, h bar over 2, minus an h bar over 2 onto that same thing. I'm not gonna bother writing it, but it would be this whole thing. If I factor that out of that, I get the same thing I started with. Does that make sense? And any way I can simplify that?
H bar over 2
And you
minus
really,
H bar
really
over 2
figure
is
that h
1.
bar over 2 minus h bar over 2 ought to cancel. And yeah, they do, but yeah, you're right to be nervous. Yes, that's gonna be 0. So, there's my wave function times 0. So what is that telling you about the spin of this combination? Well, if it's in this up state, S1 on 1 up gives you plus h bar over 2, and so we said earlier that it's in that state. That's the state it's in. This state represents particle 1 being up. What does that tell you? Particle 1 and 2 are now in a minute ago, we put them in a state where they were plus 1. And then we put them in one where they were minus 1. So now where are they? 0, yeah. And so your instinct might be to say this. And for reasons that I'm not going to get into, if I go through here, I can figure out the total spin of this combination, and it's not 0. It's the same as the other two. But I have a z component that's positive. I have a z component that's negative. What's another way of having a z component?
Having a 0 z component.
0 z component, even though my vector is not 0, right? So I can either have them both have a z component up, they can both have a z component down, or they can have a z component that cancels. But they don't cancel and give you 0 momentum, and that's what I was trying to hit there. This combination, because it's got a plus sign in there, has a non-zero spin, and it's got the same spin as the other two for that matter. It's just that it has 0 z component. There. So, do this. Give you a second to write that down, but all I've done is instead of adding those two particle functions, I'm taking the difference between them. You're going to get the same thing. You're going to get 0 onto the same wave function for just the reasons we showed. But in this case, this state is going to have 0 total orbital angular momentum. So, whereas before, we had 3 possibilities. Total angular momentum positive along z, 0 along z, minus along z. Now we have a total orbital spin angular momentum of 0. I think I said orbital before. I shouldn't. We're not talking about any orbital momentum yet. This is all spin. And I'm trying to get ready to talk about isospin. Isospin is like spin. So that's why I'm spending a little extra time on this. Now, though, we have 2 that do cancel, right? It's like the one spinning this way, the other spinning this way, so that their total spin angular momentum is 0. And then that means their z component is automatically 0. It better be 0, right? If you have 0 spin, you cannot have any z component. So, again, just to recap what we have. So, anything I'm going to erase this stuff on below. Is that all right? Okay, so in the case where the spins add, we've got three combinations. We have the up 1, up 2, up 1, up 2 plus, no. We've got three of those. Total spin is 1. And that spin can be with the z-axis, perpendicular to the z-axis, or against the z-axis. There's one case where we can think of the spins canceling. S equals 0, and that was up 1, down 2, minus down 1, up 2.
Should that be S equals 0?
It sure should. Thank you. Again, showing that it's S1, showing that it's 0, I'm not bugging you guys with that. I'm just asking you to take my word for that. So, we got 3 of these and 1 of these. What do you want to call this 3 state, that 1 state?
Triplet state.
That's exactly what those are. That's the triplet state that you're used to if you're in chemistry. And this is the singlet state. Now, we're going to exchange these particles. What does it mean to exchange particles? Well, they're going to swap. They're going to change places. We can do that one of 2 ways. So let's exchange this singlet state. Now let's do this one first. It's going to be easy. It's not going to be obvious what we're doing, so let me do this. When I exchange, I can either leave the labels and change the state. So the state would be see what I did there? I don't know if you can do that in color. I have my marker. What I did is I changed the state of this particle for this particle. Left the labels the same. Or I can do this. I can leave the states alone and exchange the labels. Should have used the red. Is that, can y'all tell that the blue and the red or the black are different? I'm not getting a lot of enthusiasm. Better?
So,
or is it's just hard?
it's just hard.
Yeah, it's just,
So,
I get that.
let me make sure I'm doing this right. So I put the lines everywhere. So,
Sure. Yep, so you kept the state in the same place, changed the label,
yeah.
or moved it to the other place and kept the labels the same.
Thank you.
So what happened, oh, and don't let this bug you. Well, tell me that. Tell me whether those are the same or not. And in this case, they seem the same, right? Here you might worry a little bit because the two's in front, but remember, the S1 operator can go past this to hit 1, and the S2 operator goes past the 1 to hit to spin particle 2. So that's not a problem. That ordering is unimportant. That's why it's almost important. It's really important to either label them all the way, which is what I tried to do. Some books, they just say, just remember the first one's 1 and the second one's 2. And in that case, it's always going to be 1, 2, and when you change the states, you're going to do it that way. But the main thing to note is what happened to this function when I exchanged it. When I exchanged the particle, what's different about that ket? Well, it looks different to me, but all of this labeling has to be a trick because we know you can't label particles, right? You can't tell them apart. So how do I get away with giving them names? The names don't matter. If I apply my operator to this, I get the same result as if I get this, as if I do it to this. I get exactly the same result. What that means within the formalism is that if I do an experiment to measure the z component of this, I will get the same number as if I measure this, as if I measure that. When you do these operators, you get numbers that have to correspond to experimental results. That's the whole point of these special operators. That's why they get special treatment. So, this state was the same under exchange. It is properly called symmetric, and you will sometimes see it called even. But symmetric is the right way to talk about it. How about this middle one? Tell me what happens when I do that one. Tell me what to write down. And we'll do it both ways, so tell me the first one and then the second one.
So 1 up, 2 down.
So, up, yeah, I'm starting with this one.
Mm-hmm.
So what would that be if I changed it? If I exchanged the particles. So there are two possibilities. One, you can exchange the states, or you can exchange the labels. Maybe change the labels this way, and that'll make life a little bit easier. So I don't change the state, it's up. What do I change? I change the label. So what does 1 become?
2.
2, very good. I have a down state that I don't change, but I label it
1.
1 plus, what motif are we using?
So it's
Leave
going
the
to be
state
down.
alone. Change the
That's gonna
label.
be 2. And that one's going to be up, but it's going to be 1.
Right. Is that the same? Down 1, up 2 is really the same as down 1, up 2, plus, this is not me exchanging, this is just me rewriting this one. Right? Down 1, up 2, plus, down 1, up 1, down 2. How does this compare with that?
It's identical.
It is identical. So would you say that is symmetric under exchange of particles? Yes, you get the same thing back, it is symmetric under exchange of particles. What do you bet's gonna happen with that one?
It's also gonna be symmetrical.
Yes, right, just switch the 1 and the 2. Go through this one and play that other game, maybe with a colored pen or something like that. See if you could do the other way, leave the labels the same, but switch the states. And you should get here, but I think it's a useful exercise to go through this a little bit and see what's going on. So what did we just find out about the S = 1 triplet state under exchange of particles?
Same under exchange?
Yeah, same one, all the way. It's the same, it's symmetric under exchange of particles. The triplet state is symmetric under exchange of particles. What do you bet you're gonna find out when you do the singlet state?
It's not gonna be symmetric.
Say again?
It's not gonna be symmetric.
It's gonna be anti-symmetric. It's gonna be minus times what you started with. So that's called anti-symmetric or odd under exchange. So these are spin states. I have two electrons and they each have spin 1/2, and this is what can happen when I have those two electrons together. So when I put them in a helium atom, that's what they gotta do. You can't have electron 1, you can't have electron 2. Their spins have to do this. So all that business about, their spins have to be opposite, that's not really what they mean. What they mean is they need to be in either a singlet or a triplet state, and they have to be in these weird combinations. So, for example, if it's in a singlet state, they write it this way. And actually, in this case, I guess that actually works because it really is spin 0. But a triplet state, it's a linear combination of states. I guess that's the point I'm trying to make. It's not, electron 1 is not spin down, electron 2 is not spin up. It's in a linear combinations of up 1, 2 down, etc. And that's that singlet state that I erased already. But there's also a space wave function. And that can be as complicated as you want. And those are essentially the energy states. All those energy electron states on the table there. Those are radial and angular spin functions. Radial and angular wave functions. We know that the radial function, how far an electron is from a proton, tells you its energy. Some of that energy will be angular, and that's what those spherical harmonics were about, the YLMs. L mattered, right? That was the orbital angular momentum. J was total, S was just spin, so that's why parity depended only on L, because that had to do with the space. So it can get really complicated, and we're not gonna go there. I'm gonna try to short circuit that. So, the simplest electron type wave function you can think about is one that decays exponentially. So this is a space wave function as a function of R, how far you are from that electron. And that says the electron is mostly here, and the farther away you go, the less likely you are to see it. That's that wave function going away. And again, if you wanted to know about angular momentum, you need to know the angular part of the wave function and so on and so forth. That's everything you need to know. Everything you can know, you're allowed to know, is in that wave function. So now I'm going to take that wave function and bring another electron in. If they're far enough apart, then nothing happens. So that's the idea that a particle way over there can be in exactly the same state as a particle way over there, because their wave functions are so far apart they don't know that they're in the same state. The only time they can know that they're in the same state is when they get close enough that the wave function of one has about the same value as the wave function of the other. So put them closer together. So you can see, right? You've got the green electron and the black electron. And I can tell them apart. Is that okay? It is okay? Why is that okay?
Oh.
Yeah.
No,
Because they're
it's not okay.
It's not okay because they're identical. And they're distinguishable if one's over there and one's over there. One's in Laranja and the other's in New Orleans, absolutely no problem. They're distinguishable because they're really far apart from each other. But they're identical, so that means when they get close enough, they become indistinguishable. Now I can't label them. So I've got to put them in a linear combination. So this is, I'm going to add them. There's my addition of the two wave functions. And then I can subtract them. I can add one plus the other, right? Sorry, this is electron 1 plus electron 2. I can also do electron 1 minus electron 2, just like I added and subtracted my spin wave functions. So when I do that, it looks a lot alike until I get here. I'm adding minus green electron. This is symmetric, because if I change the green for the black, I get exactly the same function because I'm adding them. If I relabel the black electron as the green electron and the green electron as the black electron and add them, I still get blue linear combination electron. But if I add if I change black electron and green electron in this minus combination, it will be anti-symmetric. See if I can write that. I'm not getting the glow. What do I need? Green, black, and blue. Green, blue. I'll write this symmetric over again. So I'll have black electron and green electron. Add them, I get blue electron. And that function is symmetric. Now I'm going to do the other combination. I tell you what, let me do this. Let's exchange those particles. Tell me how to draw black electron if I'm exchanging black for green. Where's black electron gonna be? On the other side, perfect. And where is green electron gonna be?
On the left.
On the other side. And what do I get when I add that combination?
The same.
Exactly the same thing. I get blue electron. Blue electron pair. I guess that's a pair of electrons. Now let's do the other one. But instead of black plus green, it's going to be black minus green. I've got to add negative green. Where's negative green going to be? It's going to be like that. So what happens when I add those? Well, here it's going to look. It's going to go here. It's going to go to 0. It's going to go down. That's what I tried to draw over there. Now let's exchange those particles. What is black electron gonna look like?
It's gonna be in the fourth quadrant.
Yep. What's green electron gonna look like?
It's gonna be in the second.
Isn't that going the way I thought? Getting the same thing.
Should black be in the first quadrant and green be in the third? Because when you switch them, then flip.
Yep. Thank you, good save. So, what you and I did was we did it twice. We switched labels and changed the states. What you and I just did, and I was a willing participant. But that would be like if I wanted to switch this, if I went to switch the state and switch the label.
And
Switch the
find out
state
same thing.
and switch the label. Now you're back where you started from. So he's right. We need to switch one of those, but not both. So actually, what I could do is switch the labels, which would mean change the colors. No, just switch, take the difference the other way. So this will be, he's right. Take that one down, that's minus this one plus the other one. Green. And I get the negative of that wave function. It's anti-symmetric, and that's really what I'm looking for. So, where are we? Generally, I'm gonna have a wave function. My total wave function will be a space part times a spin part. Very generally, I can separate out the spin and the space because they're like, the space part of the wave function is here with us in real space, and the spin function, we don't know exactly what that is. We like to think of it in terms of spinning around, but it really isn't. So, now you could ask yourself, if I exchange the particles, what could possibly happen to the wave function? The total overall wave function. What are the options? Because we've seen that a space function can be symmetric or anti-symmetric. We've seen that a spin function can be symmetric or anti-symmetric. So what are the possibilities if I exchange particles for this total wave function, the space and the spin part? And we're gonna add more, so be ready. Well, what are the options? What could happen to the space function if I exchange particles?
It can stay symmetric,
It could be symmetric, or
anti-symmetric.
it could be anti-symmetric. Spin function, what are its options? Symmetric or anti-symmetric, right? And the product will be either symmetric. Symmetric times symmetric is symmetric. Anti-symmetric times anti-symmetric is also symmetric. That seems sort of intuitive. If either of them is anti-symmetric, then if either of them is anti-symmetric, then the overall wave function, if either but not both, then they are together, the total wave function is anti-symmetric. And it turns out, for reasons that I don't understand, but maybe somebody does, although if they do, they're not talking, that fermions are anti-symmetric and bosons are symmetric. And we're going to be talking about fermions mostly coming up. So what's a fermion? Spin 1/2 particle. Why are fermions spin 1/2 particles? Because they're antisymmetric wave functions. Why are fermions antisymmetric wave? Well, they just are. I think that's where we are. Again. And they talk about it in very complicated ways, and I'm willing to give them that. I have absolutely no doubt that they know way more than I do about it. But it's not obvious to me that it's not restating that fermions are antisymmetric wave functions. Bosons have symmetric wave functions. Fermions have half integral spin, so 1/2 works, but also 3 halves, 5 halves, etc. Bosons have spin 0 or 1 or 2, etc. They have integral spin. And they behave differently. Let us consider a singlet. So you talk about if you had a system, you have fermions, electrons. We're going to erase. I'm going to erase that. Erase that. Suppose that you had a singlet spin state. What can you tell me about the space state? Singlet spin. And to look back and ask yourself, what is the symmetry of a singlet state? Antisymmetric, or asymmetric also works. So asymmetric, anti-symmetric. So what does that tell me? What do I now know if I'm in the singlet spin state?
Space has to be symmetric.
I'm in a symmetric space state. That was this one, where I've accentuated that pile up in the middle. What if I'm in the triplet?
Symmetric.
That is a symmetric spin state. So what does that tell me about my space wave function? My space state? Anti or asymmetric? And tell me this, the 2 electrons in the singlet state, do they tend to be closer together? Electrons in a singlet state. No?
I don't think so.
Well, compare it to the triplet state. What does this space wave function do when I'm here?
0.
Which is when they're close together. It's pretty small, right? The wave function is kind of small there. So they tend not to be around each other, near one another, when they're in this triplet state. What about here? Yeah, they're most likely to be in their own lane, but look, they spend a good bit of their time in between there, near one another. Well, what happens to 2 electrons if they're close together? 2 positive charges get close together. What happens to their electrostatic energy?
I just said they repel.
They do repel each other. Another way of saying that is that they raise their energy when they get close together. Which of those states has a higher energy, singlet or triplet? Turns out to be the singlet state. That singlet state is higher. So when you try to translate, make a transition to a singlet state, it takes more energy than it does to get to a triplet state. Problem is, a triplet state, there are other reasons those are tough to get to, but they're definitely lower energy. So when they draw these, they'll talk about the transition to a singlet state here, and there'll be a triplet state over here that's lower energy. That's why. Because where you have triplet states, the electrons just tend not to hang around each other. So that, you call that the exchange force, the exchange repulsion. That's not a repulsion. There's no force there. That's just a property of symmetry requirements. When you say the wave function must be antisymmetric for a fermion, they tend to stay apart from each other. And again, it's called an exchange force, but it's not a force. It's not one of the four. I thought a lot about that. I tried to figure out what exactly is going on there. But it is empirically true. So that's what I have to say about that. All that was an example. Where we're going to talk a lot about is what's the symmetry of the space wave function, what's the symmetry of the spin wave function, what's the symmetry of the isospin wave function, what's the symmetry of the color. We're going to have a long row of those, so be ready. So that gets us back to where we were, iceberg. And I had to find this to see if I can find it again. He's talking about proton-proton scattering. And proton sitting still, and you just send another one banging into it as hard as you possibly can. And I'm trying to find what that. Try to do it from memory. You characterize these states L 2s plus 1 J. So for example, and this is kind of where I left off. We sort of went off the rails a little bit. And so we talked about this. And then we have 3D1. So if you go to page 630, there's a note 2, and it says the exclusion principle prohibits interaction in certain quantum states. And these are two particle states. You got a proton, proton, fermion, fermion. They're going to interact with each other. All the stuff we've been talking about applies. So he talks about that one. So what is that state? Well, according to this motif, that's 3. 2s plus 1 is 3, 2s is 2, s is 1. So that's an s equals 1 state. What is L? 2. And J equals 2 minus 1. Tell me what the symmetry of that state is. S equals 1.
State.
It is the triplet state. Very good. It's the triplet state, which means it's symmetric. L equal 2 tells you about the space wave function. That's related to the parity. The L equal 2 state, if you go back and look at the YLMs, the parity, which is inversion, is for two particles. Inversion is the same as having, reflecting across the axis. So this, if I reflect across the axis, exchanging these two particles is the same as flipping across the axis. That looks the same. This particle, this combination of two particles, exchanging the two particles is like flipping across that axis. That's odd. Even, symmetric, odd, antisymmetric. And so this L equal 2, we know is -1 squared is +1, so that's also symmetric. That was the parity that we talked about before, but for two particles, parity is the same as exchange. So we have a symmetric space function, L equal 2. We have a symmetric spin function, triplet, S equals 1. So when can you put a fermion, two fermions, in a wave function that is symmetric under exchange of particles? It's a trick question. Fermions, total wave function has to be. If you did your experiment and you saw this, and you saw evidence of that, and you could convince people, that would be news. And at this point, that's not where the smart money is. At this point, we're pretty sure that this works and this works. So, fermions, antisymmetric, so you're not ever gonna see that interaction. You're not gonna see, no matter how much energy you have, you're not ever gonna see that interaction. So, go through, in that note 2, he lists all the ones that are not gonna work. Make sure you can articulate why each one of those doesn't work. Each one of those has the wrong wave function symmetry. And so, for example, 1p1 is not allowed, but 3p0 is. 3p0 is the two particle state above. We talked about the ones that are possible following the system can be any one of the following quantum states, and he goes to list a whole bunch of quantum states. Decode what S is, decode what L is, and that's how you're going to be able to say, yes, symmetric wave function, symmetric space, antisymmetric spin, etc. So next topic, he talks about isospin. The idea here is, he talked about talking about deuterons, but isospin is sort of a quantity that you talk about baryons in general. Ultimately, it has to do with quarks, and I don't know that we're going to go there. Most because I don't really understand. But just following along with him, I have a di-neutron or a di-proton. If I want them in my symmetric, if I want them to bond, they need to be in my symmetric spin. If I exchange the neutron for the neutron in space, it's going to be the same, right? You have two neutrons. Neutron number 1, neutron number 2, you swap them. That looks the same. Doesn't matter where they are, because they're absolutely identical. So you have a symmetric wave function. I exchange these two particles. What do you know about the overall wave function?
Symmetric, right?
The overall, they're fermions, so the overall wave function has to be antisymmetric. And if it's symmetric in space, then they cannot have an S equal 1 state. Because that's also so then when he talks about the dineutron and the diproton, why they don't form, that's figure 1714. And why the diproton and the dineutron don't form. You can't get a low enough energy. You can't get them close enough together. Deuteron has S equal 1, so a neutron, proton, they can have a symmetric wave function overall. Because they're not identical particles, so there's no rule about them. So essentially, the dineutron and the diproton, because of the symmetry of their wave function, they can't get close enough. The symmetry of the wave function has that gap between them, so they may not get close enough to bond because of the symmetry requirements for these identical particles. But, the deuteron, which is a neutron and a proton, there is no symmetry rule. They're distinguishable particles, right? I don't have to pretend that I can't tell the difference, because I can tell the difference. So that's sort of the thing to take away from that. 17.3 is talking about isospin. I'm going to talk about linear combinations of states. We're talking about even and odd functions. And sort of build the idea of what isospin is helping you figure out. And again, it's trying to bring order out of this multitude of particles. And it starts with something simple like a proton and a neutron and bonding them together. And then we'll try to look inside. I'm going to see the eclipse. You should too. I will be on my way back on Tuesday.
Okay, has to skip
So
school.
we will have an asynchronous online learning opportunity. We will not be in this room on that day. So I guess that's the 9th. So the Tuesday after the break.
That Tuesday we won't be in this classroom.
I will not be in this room. You may. And I will come up with something for you guys to work on to satisfy the bean counters. I mean, to fully embrace the learning opportunity. I'll think of something to work on. One thing I want to write up is that neutrino calculation. I think I can do a better job than I did in the room. It's wrong, but I think it's interesting.